Now we turn to depth-first search, the recursive version. Instead of a queue, it uses the call stack. It dives deep along one path before it spreads out. Now the DFS pseudocode, again in the CLRS style and zero-indexed. Time is a single counter shared across the whole walk. The first procedure sets things up. For each vertex v, we mark visited at v as false and parent at v as null. Then we set time to 0 and call DFS visit on the source. The second procedure, DFS visit of u, does the real work. It marks visited at u as true. It increases time by 1 and records that as the discovery time of u. Then it looks at each neighbor v of u if v is not visited. It sets parent at v to u, and calls DFS visit on v. That recursive call is one more frame on the stack. After every neighbor is handled, it increases time by 1 again, and records that as the finished time of u the shape matches Chapter 8's recursion template, a base case when no unvisited neighbors are left, and a recursive case that is one more call. Let's try a prediction. This is the same graph as before, with the same neighbor lists in ascending order. But DFS does not use a queue. It uses a stack through recursion, so it dives deep first instead of spreading out wide. Here is the question. In what order are the vertices discovered? Follow the first unvisited neighbor each time and only back up when you hit a dead end. Pause the video and write down your order starting at 0. Here is the answer, 0, 1, 3, 2, 4, 5. From 0 we dive to 1. From 1 we take its first unvisited neighbor 3. From 3 we take 2. From 2 we take 4. From 4 we reach 5. One long plunge with no backtracking needed until the very end. The cave, not the pond. Let's trace the DFS recursion, one event at a time. The stack grows one frame each time we follow an edge and shrinks one frame each time we hit a dead end. Red is the top of the stack. Teal means still on the stack. Green means finished. We start with an empty stack. The table on the right will add one row for every push and every pop, and keep every row. We enter the DFS visit for vertex 0. It goes on the stack and turns red. Vertex 0 gets discovery time 1. The visit order starts with 0. 0's first unvisited neighbor is 1, so we call the visit for 1. A second frame pushes on. 1 gets discovery time 2, and now 1 is the top of the stack. From 1, the first unvisited neighbor is 3. We push a frame for 3, with discovery time 3. The walk is plunging deeper. From 3, the first unvisited neighbor is 2. We push a frame for 2, with discovery time 4. From 2, the first unvisited neighbor is 4. We push a frame for 4, with discovery time 5. From 4 we reach 5. We push a frame for 5 with discovery time 6. The stack is now 6 frames deep. This is the deepest point of the whole walk. Now the unwind begins. Vertex 5 has no unvisited neighbor, so it is a dead end. Its frame closes with finish time 7 and pops off. 5 turns green and 4 is the top again. 4 has nothing left to visit either. It finishes with finish time 8 and pops. 2 is back on top. 2 finishes with finish time 9 and pops. 3 becomes the top of the stack. 3 finishes with finish time 10 and pops. Only 1 and 0 are left. 1 finishes with finish time 11 and pops. Vertex 0 is alone on the stack. And finally 0 finishes with finish time 12 and pops. The stack is empty and DFS is done. It grew on the way down and shrank on the way back up, one frame at a time. Here are those same 6 pops as table rows. Return 5, finish time 7, and the stack drops to 0, 1, 3, 2, 4. Return 4, finish time 8. Return 2, finish time 9. Return 3, finish time 10. Return 1, finish time 11. And return 0, finish time 12. The stack is empty. Now look at the last column. The discovery order never changed during the whole unwind. Discovery order is fixed on the way down, and at every row, the stack contents are exactly the vertices on the current path from the source. Each child's discover and finish interval nests inside its parents, which we read as numbers in 2 slides. This is the same walk as before, but now drawn on the graph itself instead of the call stack. The green path is the route the recursion actually took, 0, 1, 3, 2, 4, 5. The teal vertices 0, 1, 3, 2, and 4 are already discovered and still on the call stack. Each one has a live frame scanning its neighbors. The red vertex 5 is the current frame, just entered. The dashed gray edges exist in the graph, but the walk did not take them because their other end was already visited. This is the key idea. The path from the root down to the deepest live frame is the call stack, read from bottom to top. The picture on the graph and the picture on the stack show the exact same 6 frames. This table collects the timestamps from the trace we just watched. Each vertex has a discovery time when its frame opened and a finish time when its frame closed. Vertex 0 opened first, so its discovery time is 1. It closed last, so its finish time is 12. Its interval runs from 1 to 12. Vertex 1 has discovery time 2 and finish time 11. Its interval from 2 to 11 sits completely inside 0's interval. Vertex 5 is the deepest one. It opened at time 6 and closed at time 7. Its tiny interval sits inside every ancestor above it. This is the nesting property. Every child's interval sits entirely inside its parent's interval, just like a matching set of parentheses. It is the same fact as the recursion stack. Whoever is still open, with a bigger interval, is still an ancestor. This is the recursive DFS in C. It matches the pseudocode line for line. The function is called DFS visit. It takes the graph, the current vertex U, and the bookkeeping arrays, visited, parent, discovery times, and finish times. It also takes a pointer to the shared time counter. First, it marks the current vertex as visited. It sets visited at U to 1. Then it records the discovery time. It adds 1 to the shared time counter, then stores that value in discovery at U. This is the moment the frame opens. Now the loop walks the adjacency list of U. It stops at the nil marker, which is the end of the list. Each time round, it reads the next neighbor into V. It checks whether V is still unvisited. If V is new, it records that we reached V from U. It sets parent of V to U. Then it calls DFS visit on V. This is the recursion. One more frame goes on the stack, and we dive deeper. When the loop is done, every neighbor has been handled. It records the finish time. It adds 1 to the counter again and stores it in finish at U. This is the moment the frame closes. The total time is big O of V plus E. Each vertex opens exactly 1 frame, and each edge is examined once from each end that touches it. This is what the program prints. Each row shows 1 vertex, its parent, its discovery time, and its finish time. Vertex 0 is the source. Its parent is -1, which means it has no parent. Its discovery time is 1, and its finish time is 12, just like the trace. Look at vertex 2. Its parent is 3. That matches the trace. Vertex 2 was discovered while the frame for vertex 3 was open. The numbers on the screen are the same numbers we watched on the stack.